Hello, this is Dan Donahue's project report for the MENS 5001 optimization course. My chosen project was to optimize the shape of an aircraft using CAD and CFD software. I was looking to optimize some of the performance parameters of the aircraft through a particle swarm optimization scheme. Specifically, I was looking to optimize the lift-to-drag ratio by extracting those coefficients through CFD cases. To do this, I had to create an initial three-dimensional model of a baseline configuration. This was done through the use of the SOLIDWORKS CAD software available on the WashU computers. I then used the design table feature to turn the baseline configuration into a rubber model by allowing for several of the design parameters to be changed through this design table. After setting minimum and maximum bounds on each of the design variables, I was able to create an initial generation using the random number function in Excel. These 10 initial models were then the population size of my initial generation. CFD was then used to determine the maximum lift-to-drag ratio for each of these models in the generation. Then subsequent generations would be adjusted towards the best model of the previous generation, thus advancing the population towards an optimum solution. I chose to have 8 design variables, 4 used to define the wing and 4 used to define the V-tail. These two renderings show the minimum and maximum bounds allowed on each variables and are tabulated on the previous chart. The models of the initial generation would all fall somewhere in the spectrum between these two renderings, and future generations would all move towards an optimum solution within these two bounds. To evaluate my fitness function, I ran 3 ANSYS Fluent CFD cases for each model in the generation. Realizing that drag can be modeled as a second-order polynomial of lift, I was then able to determine a maximum lift-to-drag ratio for each of the models within a generation. The model that contained the maximum of all of these lift-to-drag ratios was then used in the scheme to evolve future generations. Shown here are the renderings for the first generation, as well as their determined maximum lift-to-drag ratios. Model 4 in this generation had the maximum L over D ratio and therefore was used as the advancing model for the population. All the models in the second generation had their design variables moved towards the Model 4 design by some random number. The renderings for Generation 2 are shown here to have all been adjusted in this manner. Once run, it was determined that Model 4 was again the best fit. The third generation also had Model 4 as the best lift-to-drag ratio. The fourth and final generation brought with it a new best model, but this was the final generation as described on the next chart. As the generations evolved, the average lift-to-drag maximum increased as expected. The maximum lift-to-drag ratio was held for the first 3 generations, which was a product of the initial generation containing a random model near the optimized lift-to-drag ratio. The stopping criteria I used for generational evolution is shown and is a function of the average lift-to-drag and maximum lift-to-drag becoming close to one another. This essentially shows convergence towards the optimum value. Even though the maximum lift-to-drag ratio started to increase in generation 3, I chose to stop the iterations. This was because I had met my stopping criteria set and because it takes a lot of time to run the CFD cases. If a more optimum solution were desired, the generation population sizes could be increased to allow for more data points. Also, the convergence criteria could be set lower and more generations could have been run. To do this, I would suggest using automation on top of this optimization. By writing scripts to automate the CAD and CFD process, the process could be made to be hands-off. This project could be taken a step further by including more design variables to better describe the shape of the aircraft. Different types of rubber models could also be tested to optimize different aircraft shapes. On top of this, finite element analysis could also be used to optimize the structure even more. Through CFD, the loads on the aircraft could be determined. Finite element analysis could then be run to see what types of materials should be used or to help define the interior structure of the aircraft. It would be very interesting to see what sort of aircraft shapes would be made by optimizing for both aerodynamics and structural design variables. Thank you.